Hello, and welcome to the Dreamy Science Lab, your peaceful little pocket of the universe where wonder feels soft and the night quietly cradles you. Before we slip into tonight's journey among the stars, I'd love to hear from you. Where in the world are you tuning in from right now, and what time is it where you are? Drop it in the comments below. I'm always quietly amazed at how many of us are gently floating awake together across so many different time zones. And if tonight's story helps you feel calm or sleepy in the best way, a soft little like and maybe a subscribe would mean the world. It helps other tired souls discover this quiet corner too. Tonight we're going somewhere beautiful, the quiet unfolding of the universe. From the very first moment of the Big Bang to the gentle ignition of the first stars, all emerging from warmth, darkness, and infinite space. I hope it's peaceful enough to guide you towards sleep. But if your thoughts decide to wander instead, at least you'll carry a few wonders of the cosmos into your morning. So come a little closer. Let your body sink into comfort. Take a slow, unhurried breath. Together we'll drift from the universe's first light to the birth of the earlier stars. No rush, no expectations. The cosmos has all the time in the world. Ready? Let's begin. You've found a quiet place. Maybe it's late at night. Maybe the world outside has finally gone still. The noise faded, the demands quieted. Maybe you're looking for something gentle to fill the silence. Something that asks nothing of you except to listen, or not listen, to drift, to rest, to simply be. It's impossible, isn't it? Our minds can't really grasp it. We think in terms of things, objects, space, time. Even when we imagine emptiness, we imagine it as a space where things could be, a stage waiting for actors. But before the Big Bang, there was no stage, no waiting, no potential even, just nothing. Just a tiny amount. A trace. Parts per million maybe, but enough. Enough to change how stars formed. Enough to allow smaller stars, longer-lived stars, enough to allow planets, rocky worlds, with iron cores and silicate mantles and atmospheres of nitrogen and oxygen. Gas giants, with cores of rock and metal beneath thick envelopes of hydrogen and helium. Moons, asteroids, comets. The universe was becoming more interesting, more diverse, more complex. Let's zoom out for a moment. We've been focusing on individual stars, the first lights in the darkness. But stars don't exist in isolation. They gather, they cluster, pulled together by gravity, organized by rotation and momentum, they form galaxies. At first, in the very early universe, there were no galaxies, not as we'd recognize them, just loose collections of stars, small groups, proto-galaxies, irregular, chaotic, still forming, still gathering mass. But over time, hundreds of millions of years, they grew. Small proto-galaxies merged, collided, combined into larger structures, and structure emerged. Some galaxies spinning rapidly flattened into disks, spiral galaxies, with graceful arms curving outward from central bulges. Others, formed from more violent collisions, became smooth and featureless, elliptical galaxies, spherical or egg-shaped. No disk, no spiral structure, just a smooth distribution of stars, and some remained irregular, lumpy, asymmetric, still chaotic, never settling into a regular shape. Our galaxy, the Milky Way, formed about 13 billion years ago, not all at once, gradually, piece by piece. Small proto-galaxies merged, gas clouds collapsed, stars formed. Over billions of years it grew, it assembled, it took shape. Now it's a spiral galaxy, a majestic disk of stars about 100,000 light-years across, with a central bulge, a dense sphere of old yellow stars, with spiral arms, curved regions of enhanced star formation, outlined by young blue stars and glowing gas clouds, with a halo, a spherical region surrounding the disk containing old stars and globular clusters, and at the very centre, a supermassive black hole, about 4 million times the mass of the Sun, quiet now, dormant, and yet somehow from that nothing everything emerged, not slowly, not gradually, in an instant, a singular, impossible, creative instant. The universe began, but in the early days, when gas was still falling into it, it blazed like a beacon, a quasar, one of the brightest objects in the universe, visible across billions of light years. The Milky Way spins, slowly, majestically. At the location of our Sun, about 26,000 light-years from the galactic centre, the orbital speed is about 515,000 miles per hour. That sounds fast, and it is. But the galaxy is so large that it still takes us about 230 million years to complete one orbit. The last time we were in this exact spot, dinosaurs were just beginning to appear on Earth. The next time we're here, they'll have been gone for hundreds of millions of years. The galaxy's timescale is so vast it makes human history, all of recorded civilization, look like a single frame in an endless film. The Milky Way contains somewhere between 100 billion and 400 billion stars. Let that sink in for a moment. Billions of stars, each one a sun, each one potentially surrounded by planets, and we're just one galaxy. There are approximately 2 trillion galaxies in the observable universe, each containing on average hundreds of billions of stars. The total number of stars in the universe is estimated to be around 10 to the power of 24, a 1 followed by 24 zeros, more stars than grains of sand on all the beaches on Earth. More stars than seconds have passed since the Big Bang. More stars than anything you can meaningfully imagine. And most of them have planets. We know this now. We've detected thousands of exoplanets, planets orbiting other stars, and the data suggests that nearly every star has at least one planet, which means there are trillions upon trillions of worlds out there. Rocky worlds like Earth, gas giants like Jupiter, ice giants like Neptune, super-Earths, mini-Neptunes, hot Jupiters orbiting impossibly close to their stars, rogue planets, drifting through interstellar space with no star at all, an unimaginable diversity of worlds, and on some of them, maybe many of them, there might be life. We don't know yet. We're looking, searching, listening. Projects like SETI, the search for extraterrestrial intelligence, scan the skies for radio signals that might indicate technological civilizations. 13.8 billion years ago. That's how long ago the Big Bang happened. We know this. We've measured it. Not perfectly. There's some uncertainty, a few 100 million years give or take, but we know. We can calculate back using the expansion rate of the universe, the ages of the oldest stars, the density of matter and energy. Missions like the James Webb Space Telescope analyze the atmospheres of exoplanets, looking for biosignatures, oxygen, methane, combinations of gases that, on Earth, are produced by life. So far, we haven't found anything, but the search is still young. We've only just begun, and the universe is vast, patient. If there is life out there, and statistically it seems likely, we'll find it eventually, or they'll find us. But even if we're alone, even if Earth is the only world with life in the entire observable universe, that doesn't diminish us. If anything, it makes us more precious, more significant. We'd be the only place where the universe has become aware of itself. The only place where matter has organized itself into something that can think, feel, create, love. The only place where questions can be asked. That's not insignificance. That's extraordinary. Let's come back to stars, these lights in the darkness, these engines of creation. Let's talk about their lives, from birth to death, from ignition to extinction. Because stars, for all their seeming permanence, are temporary. They shine brightly, yes, they seem eternal, unchanging, but they're burning fuel, and eventually all fuel runs out. A star's life, its duration, its evolution, its ultimate fate, depends almost entirely on one thing: its mass. How much material it gathered when it formed. How much hydrogen it has to burn. Small stars live long, quiet lives. Massive stars live brief, violent ones. Let's start with the small ones. Red dwarfs. These are the smallest true stars, about 0.08 to 0.5 times the mass of the Sun. Dim, cool, red in colour, hence the name. They burn their hydrogen slowly, very slowly, so slowly that even the oldest red dwarfs, formed in the early universe billions of years ago, are still on the main sequence, still burning hydrogen, still shining. They could burn for trillions of years, 10 trillion, 20 trillion, maybe longer. 13.8 billion years. It's a number so large it loses meaning. Try to count to 1 billion. Just count. One number per second. It would take you 32 years, and that's just 1 billion. The universe is 13.8 thousand times older than that. Incomprehensible. By the time the oldest red dwarfs finally exhaust their fuel and die, the universe will be unrecognizably different. All the other stars will have burned out. The universe will be cold, dark, approaching the heat death. And these small, patient, dim stars will be the last lights in the cosmos, still shining, still warming whatever worlds might orbit them, the last embers of a universe winding down. Our sun is a medium-sized star, a yellow dwarf, about 1 solar mass by definition. It's been burning for about 4.6 billion years. It has about another 5 billion years left. Right now, it's stable, balanced. The inward pull of gravity perfectly matched by the outward push of fusion. But it's slowly getting brighter. As helium builds up in the core contracts slightly, heats up slightly, and fusion increases. In about 1 billion years, the sun will be about 10% brighter than it is now. That doesn't sound like much, but it's enough to make Earth uninhabitable. The oceans will evaporate. The atmosphere will be stripped away. The surface will become a scorched desert. Life on Earth, if any remains, will end. But the sun will keep burning. In about 5 billion years, the sun will exhaust the hydrogen in its core. Fusion will stop. The core will contract, heat up, and hydrogen in a shell around the core will begin to fuse. The outer layers of the sun, heated by this shell fusion, will expand. The sun will swell enormously. It will become a red giant, growing to perhaps 100 times its current diameter. Its surface will extend past the orbit of Mercury, possibly past Venus, maybe even past Earth. The inner planets will be engulfed, vaporized. Earth, if it survives, will be a lifeless cinder. Scorched, molten, barely recognizable. But the Sun's story isn't over. In the core, now hot enough from the continued contraction, helium will begin to fuse. Helium atoms slam together, forming carbon and oxygen. For about 100 million years, the Sun will burn helium, stabilizing somewhat, shrinking a bit from its maximum red giant size. But helium burns faster than hydrogen, and when it runs out, that's it. For a star like the Sun, carbon and oxygen can't fuse. The temperature doesn't get high enough. The pressure doesn't get strong enough. Fusion stops. The core becomes inert, a ball of carbon and oxygen about the size of Earth, incredibly dense, and the outer layers drift away, gently, slowly, blown off by stellar winds, pushed outward by radiation pressure. And yet, it happened. Time began, space began, matter and energy began. All of it, from nothing. Or perhaps not from nothing. Perhaps from something we don't understand yet. A quantum fluctuation, a collision of higher dimensional membranes, a previous universe collapsing and rebounding. They form a planetary nebula, a glowing shell of gas expanding into space, illuminated by the ultraviolet light from the exposed core. For a few tens of thousands of years the nebula glows, beautiful, colourful, red, green, blue, different elements emitting light at different wavelengths, and then it fades, disperses, becomes too diffuse to see, and all that's left is the core, a white dwarf. A white dwarf is strange, about the size of Earth, but containing about half the mass of the Sun. The density is incomprehensible. A sugar cube-sized chunk of white dwarf material would weigh as much as a car. It doesn't burn. There's no fusion, no energy source. It just glows, radiating away its stored heat, cooling, slowly, over billions of years, tens of billions, hundreds of billions. Eventually, so far in the future it's almost meaningless, it will cool completely. It will become a black dwarf, a cold, dark sphere of carbon and oxygen drifting through space, invisible, inert, a fossil, the remnant of a once bright star. But we're not there yet. The universe isn't old enough yet for any black dwarfs to exist. Every white dwarf we can see is still glowing, still warm, still visible, patient monuments to stellar death. Now let's talk about massive stars. Stars more than 8 times the mass of the Sun. Their lives are different, faster, more violent. They burn through hydrogen in just a few million years, then helium, then carbon, neon, oxygen, silicon. Each stage faster than the last. Each element fusing into the next. A massive star might burn hydrogen for 1,000,000 years, helium for 100,000 years, carbon for 1,000 years, oxygen for a year, silicon for a week, and then the core is iron. Iron is special. It's the most stable element, the most tightly bound nucleus. Fusing lighter elements into iron releases energy. That's what's been powering the star. But fusing iron into anything heavier requires energy. It's endothermic. It takes more energy than it produces. So when the core is iron, fusion stops. The energy source is gone. And without energy to create pressure, there's nothing to hold the star up against gravity. The core collapses. This happens fast. In less than a second, the iron core, about the size of Earth, collapses to about 20 kilometers across. The density becomes unimaginable, nuclear density, the density inside an atomic nucleus. We don't know, but we know what happened next. Protons and electrons are crushed together, forming neutrons. The core becomes a neutron star, and the collapse stops, rebounds. The infalling outer layers hit this rigid core and bounce. A shockwave rips through the star, travelling outward at tens of thousands of kilometres per second. The star explodes, a supernova. For a brief time, a few weeks, a single supernova can outshine an entire galaxy, billions of times brighter than the sun, releasing more energy in that brief time than the sun will emit in its entire 10 billion year lifetime. The violence is extraordinary, beyond human comprehension. But from that violence, creation. In the extreme conditions of the supernova, elements heavier than iron are forged. Cobalt, nickel, copper, zinc, silver, gold, platinum, uranium. All the elements at the end of the periodic table, all the heavy metals, they're made in supernovae, in those brief moments of unimaginable heat and pressure, and then they're scattered, blasted into space, mixed with the interstellar medium, seeding the galaxy with the ingredients for future stars, future planets, future life. Every atom of gold in every ring, every coin, every circuit board, every atom of uranium in every reactor, every nuclear weapon, every atom of silver in every photograph, every mirror. It was forged in a supernova, in the death throes of a massive star, scattered into space, drifted for millions of years, eventually gathered by gravity into new clouds, new stars, new worlds, and now it's here, on Earth, in your jewellery, in your electronics, in your body. You're not just made of stardust, you're made of supernova ash, the remnants of stellar catastrophes. After the supernova fades, what's left depends on the mass of the original core. If the core is between about 1.4 and 3 solar masses, it becomes a neutron star, a sphere about 20 kilometers across, containing more mass than the sun, spinning rapidly, sometimes hundreds of times per second, blasting beams of radiation from its magnetic poles. If those beams happen to sweep across Earth, we see pulses of radio waves, regular, precise, like a cosmic lighthouse. We call them pulsars. In that first instant, and we're talking about a fraction of a second so small it has no meaning in human terms, the universe was unimaginably hot. Not hot like fire, not hot like the sun, not even hot like the core of a star. When they were first discovered in 1967, they were so regular, so precise, that astronomers briefly wondered if they might be signals from an alien civilization. They're not. They're just rapidly spinning neutron stars. But they're amazing in their own right. Natural clocks, cosmic timekeepers, millisecond pulses are more accurate than atomic clocks. If the core is more massive, more than about 3 solar masses, even neutrons can't stop the collapse. Gravity wins completely. The core keeps collapsing, smaller, denser, more and more compressed, until it becomes nothing, a point, a singularity, surrounded by an event horizon, a boundary of no return, a black hole. Black holes are strange, eerie, fascinating. They warp space and time around them. They bend light into impossible curves. Time slows down near them. The closer you get to the event horizon, the slower time passes relative to someone far away. If you watched someone fall into a black hole, you'd see them slow down, move in slow motion, redshift, fade, but never quite reach the event horizon. From their perspective, they'd cross the horizon in finite time, but from yours, they'd take forever. And once past the horizon, there's no escape, no way out. All paths lead inward, to the singularity, to the center, to the point where our physics breaks down and we don't know what happens. Black holes don't last forever, though. They evaporate, slowly, through a process called Hawking radiation. Quantum fluctuations near the event horizon create particle-antiparticle pairs. Sometimes one falls in and the other escapes, carrying away energy. From the outside, it looks like the black hole is radiating, slowly losing mass. For stellar mass black holes, this process is incredibly slow. They'd take 10 to the power of 67 years to evaporate completely. That's a 1 followed by 67 zeros, incomprehensibly longer than the current age of the universe. But eventually even black holes die, and when the last black hole evaporates, the age of light will be truly over, hot beyond comprehension, trillions of degrees, quadrillions, numbers that mean nothing because there's nothing in our experience to compare them to. At those temperatures, matter as we know it couldn't exist. No atoms, no protons or neutrons, not even quarks at first. Just pure energy, seething and roiling, denser than anything that exists today, compressed into a space smaller than an atom. Take a breath. This is heavy material. Not intellectually, though it is, but emotionally. The death of stars, the violence, the inevitability. It can feel dark, depressing. But remember, this is how the universe creates. Stellar death is stellar birth. The two are inseparable. Every new star contains the remnants of old ones. Every new world is built from the ashes of ancient suns. Death is not an ending. It's a transformation, a return to the pool, a scattering of seeds, a giving back of what was borrowed. And from that giving, new life, new possibilities, new stories. The universe recycles itself, endlessly, beautifully, and we're part of that cycle. Let's zoom out again, way out, to the scale of the entire universe, the entire history, 13.8 billion years, from the Big Bang to now, from the first moment to this moment, from nothing to everything. If we compress that entire history into a single calendar year, 13.8 billion years squeezed into 365 days, here's what it looks like. The Big Bang happens at midnight on January 1st. The first stars ignite around January 10th. The Milky Way begins to form around January 16th. Our solar system forms, the Sun, Earth, and all the planets, on September 2nd. Life on Earth begins sometime in mid-September. Simple cells, single-celled organisms. For months, that's all there is. Microscopic life, invisible, but alive, growing, evolving. Complex life, animals, plants, things you could see with the naked eye, doesn't appear until around December 15th. The Cambrian explosion, when life suddenly diversified into many body plans, happens December 17th. Land plants appear December 20th. Dinosaurs emerge December 25th. Christmas Day, smaller than a nucleus, smaller than anything we can measure, and it was expanding, not exploding into space. There was no space to explode into yet. Space itself was expanding, unfolding, creating itself as it went. They dominate for 6 days, and then, on December 30th, they're gone, wiped out by an asteroid impact. Mammals diversify, primates evolve, humans begin to emerge. Homo sapiens, our species, appears at 11:52 p.m. on December 31st. All of recorded history, everything we've written down, Everything we remember as a species happens in the last 20 seconds before midnight. The Roman Empire rises and falls in the last 5 seconds. The Industrial Revolution happens in the last second. Your entire lifetime is a fraction of a second, a blink. We are so young, so incredibly, almost impossibly young. The universe is 13.8 billion years old. Our species is 300,000 years old. Our civilization is maybe 10,000 years old. We're infants, toddlers, just learning to walk. And yet, in that brief time, we've learned so much. We've figured out where we came from. We've traced our lineage back through evolution, through geology, through astronomy, all the way to the Big Bang. We've measured the age of the universe. We've detected the cosmic microwave background. We've discovered thousands of exoplanets. We've built machines that can see across billions of light years. Telescopes that capture photons that have been travelling since the universe was young. We've developed mathematics complex enough to describe black holes, quantum mechanics, the curvature of space-time. We've split the atom. We've walked on the moon. We've sent probes beyond the solar system, carrying messages to whoever might find them. We've done all this in a few thousand years of civilization, few hundred years of modern science. It's extraordinary. But we're still so small. A single species on a single planet orbiting a single star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. When you zoom out far enough, we vanish. We're not even a pixel, not even a speck. Earth, in the grand scheme of things, is nothing. The sun is nothing. The Milky Way is nothing. We're a tiny temporary fluctuation in the vast cosmos. And yet, we're here. We're conscious. We're aware. We can look at the stars and understand what they are. We can trace the history of the universe from its beginning to now. We can ask questions, big questions. Where did we come from? Why are we here? What does it all mean? Imagine a balloon being inflated. The surface of the balloon is space. Every point on the surface is moving away from every other point as the balloon expands. But there's no center on the surface. There's no edge on the surface. Every point is equivalent. That's what was happening, except in 3 dimensions, except faster than light, except creating time itself as it went. And we can find answers, not complete answers maybe, not final answers, but answers. We are the universe examining itself, thinking about itself, wondering about itself. We are, as far as we know, the only part of the universe that can do this. That's not small. That's not insignificant. That's profound. There's a quote from Carl Sagan. From his series Cosmos, he said, "We are a way for the cosmos to know itself." Think about that. For 13.8 billion years, the universe just was, expanding, cooling, stars forming and dying, galaxies colliding, all of it happening according to physical laws, cause and effect, no awareness, no purpose, no meaning, just happening. But then, on at least one world, maybe many, something new emerged, life, and eventually consciousness. And suddenly, for the first time, the universe could look at itself, through us, through our eyes, our minds, our telescopes and equations, and wonder. The universe became self-aware. You are the universe, not separate from it, not an observer standing outside looking in. You are part of it, made of it, woven into it. every atom in your body was forged in a star. Every breath you take contains atoms that have been cycled through countless organisms over billions of years. You're not just in the universe. You are the universe, temporarily organized into a form that can think and feel and wonder. And when you die, when your atoms scatter, return to the earth, cycle back into the biosphere, they'll become part of something else. A tree, a cloud, a river, another person. Nothing is lost, nothing is destroyed, just transformed, endlessly, beautifully. So where does that leave us? We're small, temporary, cosmically insignificant, and yet we're here. We're conscious. We matter to each other. Does anything we do have meaning? It's a good question, an important question, and the answer depends on what you mean by meaning. If you mean cosmic significance, does our existence affect the universe as a whole? Then probably not. That's what this is for. There's no hurry here, no deadlines, no tests, no expectations, just a slow, gentle unfolding of the greatest story ever told. The true story, the story of everything that exists. We're going to travel back, all the way back, further than you can imagine, to the very beginning of time itself. In the first fraction of a second, 10 to the power of minus 36 seconds, a decimal point followed by 35 zeros and then a 1. Something extraordinary happened. Inflation. The universe doubled in size, then doubled again, then again, then again. If humanity disappeared tomorrow, the stars would keep shining, galaxies would keep colliding, black holes would keep devouring matter. The universe wouldn't notice, wouldn't care. It doesn't have the capacity to notice or care. It's not conscious. It just is. But if you mean personal significance, does our existence matter to us, to each other? Then yes, absolutely, profoundly. Meaning isn't something the universe gives us. It's something we create. We care about each other. We love. We build. We create art and music and stories. We help. We comfort. We celebrate together. We mourn together. We laugh. We cry. We wonder. We learn. That matters, not to the universe, but to us. And that's enough. We don't need cosmic significance. We don't need to be important on the scale of galaxies and eons. We just need this, each other, connection, the small moments, a conversation with a friend, a shared meal, a sunset watched in silence, a child learning something new, a kind word when it's needed most. These things don't echo through eternity. They don't change the trajectory of stars, but they're real, they're beautiful, they're ours. The universe is vast and cold and indifferent, but we're not. We're warm, we're alive, we care. We create pockets of warmth and meaning in an otherwise indifferent cosmos, and in a universe that's mostly empty, mostly dark, mostly silent. That's something special. That's something precious. You don't need to be cosmically significant. You don't need to leave a mark that lasts forever. You just need to be here, now, fully, kindly, to appreciate the light while it's still shining, to love the people around you while you still can, to notice the beauty, the small things, the temporary things, a flower blooming, a bird singing, rain on the window, the way light falls through leaves. These things won't last forever, but right now, they're here, and that's enough. Let's talk about the future, not the deep future, the heat death of the universe, the evaporation of black holes. We've touched on that, but the nearer future, the next few billion years. What will happen to us, to Earth, to the solar system? Over and over, in less time than it takes light to cross the diameter of a proton, the universe grew from smaller than an atom to larger than a galaxy. Exponential expansion, faster than anything, creating space, creating time, creating the seeds of everything that would come. In about 1 billion years, the sun will be about 10% brighter than it is now. That may not sound like much, but it's enough. The Earth will heat up. The oceans will start to evaporate. Water vapor is a greenhouse gas, so that will cause more heating, a runaway greenhouse effect. Within a few 100 million years, Earth will be uninhabitable, at least on the surface. The oceans will be gone. The atmosphere will be stripped away. The surface will be scorched, lifeless, hostile. If humanity is still around, if we haven't destroyed ourselves or evolved into something unrecognizable, we'll need to leave. Move to Mars, maybe, or Europa, or Titan. Moons that will become more habitable as the sun brightens, or leave the solar system entirely, find another star, another world. In about 4 billion years, the Andromeda Galaxy will collide with the Milky Way. It sounds catastrophic, and it is, in a way. But galaxies are mostly empty space. The stars are so far apart that actual collisions will be rare. Instead, the galaxies will pass through each other. Their gravity will distort their shapes. Stars will be flung into new orbits. Over about 1 billion years, the two galaxies will merge, forming a single, larger galaxy. Probably elliptical in shape, smooth, no spiral arms, just a giant amorphous blob of stars. If the sun still exists, and it will, though it'll be well into its red giant phase, it will be part of this new galaxy. Our descendants, if any exist, will see a very different night sky. More stars, closer together, the Milky Way and Andromeda combined. It will be beautiful. In about 5 billion years, the sun will swell into a red giant. We've talked about this. Earth will be scorched, possibly engulfed. But the outer solar system will become more interesting. Jupiter's moons, Saturn's moons, they'll be warmed by the brightening sun. Ice will melt. Atmospheres will thicken. Europa might have liquid water oceans. Titan might have a more habitable environment. For a few 100 million years, while the sun burns helium, these distant worlds might be oases of warmth in a cooling solar system. And then, the sun will shed its outer layers, become a white dwarf, and the solar system will go dark, cold, frozen, lit only by starlight from the surrounding galaxy. In about 100 trillion years, the last stars will burn out. We've talked about this too. The universe will go dark. Only remnants will remain. White dwarfs, neutron stars, black holes, brown dwarfs. No new stars, no new light. The age of stars will be over. Why did this happen? We're not entirely sure. We call it the inflaton field, a hypothetical field that drove this expansion. But it's still theoretical, still mysterious. But the evidence is there, written into the structure of the universe, in the flatness of space, in the uniformity of the cosmic microwave background, in the distribution of galaxies. But even that's not the end. The universe will keep expanding. Galaxies will keep moving apart. Eventually, they'll be so far apart that light from one galaxy will never reach another. The expansion of space will carry them away faster than light can travel. Each galaxy, or rather the remnant of each galaxy, will be alone, isolated in its own observable universe, unable to see anything beyond itself, and over incomprehensible timescales, even those remnants will decay. Protons might decay. Matter might fall apart into radiation. Black holes will evaporate. Hawking radiation, slow but inexorable, will cause them to lose mass, shrink, and eventually vanish. Even the largest supermassive black holes, billions of times the mass of the Sun, will evaporate in about 10 to the power of 100 years. And then, nothing. Just empty space, expanding forever, cooling forever, approaching absolute zero, maximum entropy, no energy gradients, no ability to do work, no change, the heat death of the universe. It sounds bleak, but remember, this is so far in the future it's almost meaningless. 10 to the power of 100 years, a Google, a 1 followed by 100 zeros. The universe is currently 1.38 times 10 to the power of 10 years old, about 14 billion. The heat death won't happen for another 10 to the power of 100 years, a number so large that 14 billion is essentially zero in comparison, for all practical purposes forever. And between now and then, so much will happen. Stars will keep forming for tens of billions of years. Planets will keep forming. Life might emerge on countless worlds. Civilizations might rise, might spread across galaxies, might find each other, might communicate, might collaborate, or might fight, might destroy themselves, might fade into obscurity. We don't know, but the possibilities are there. The universe is still young, still active, still full of potential. For a long time yet there will be light, there will be warmth, there will be perhaps life and consciousness and wonder. It happened, and when it ended, when inflation stopped and the expansion slowed to a more sedate pace, the universe was still tiny by today's standards, still hot beyond imagining. But it was there, real, expanding, cooling, beginning its long journey towards stars, galaxies, planets, and you. Let's drift for a moment, out into the dark, into the space between stars, far from Earth, far from the Sun, far from the Milky Way even, out into intergalactic space, the vast empty reaches between galaxies. It's quiet here, deeply, profoundly quiet. There's no sound, no air to carry it, just vacuum, empty space, and the silence. It's old, ancient, primordial. It's been here since the beginning, since the Big Bang, since the first expansion, since the first moment. It's patient, it doesn't hurry, it doesn't worry, it doesn't wonder, it just is. In this silence, light travels, photons, billions of them, trillions, more than can be counted, more than can be imagined, streaming out from galaxies, from stars, from quasars and supernovae and glowing nebulae, each one travelling in a straight line, or as straight as possible, bent slightly by the gravity of massive objects, at 186,000 miles per second. Constant, eternal, unwavering. Some of these photons will travel for billions of years and never hit anything, never be absorbed, never interact, just moving forever through the expanding universe, red-shifting as space stretches, losing energy, fading into invisibility. Others will strike a planet, a dust grain, a molecule of hydrogen, and their journey will end. Their energy will be absorbed, converted, used, transformed. There's something peaceful about that, isn't there? The idea that light just goes. It doesn't question its purpose. It doesn't wonder if it matters. It doesn't hesitate or doubt. It just moves, steady, constant, inevitable, until something stops it, or until the universe expands so much, cools so much, that the light fades into nothingness. Either way, it does what it does, completely, fully, without regret. Out here, in the space between galaxies, you can see everything. If you could float here, impossibly, magically, you'd see galaxies in every direction. Not close, not detailed, just faint fuzzy patches of light, smudges against the darkness, each one containing hundreds of billions of stars, each one a complete universe unto itself. Let's slow down for a moment. Take another breath. This is a lot to absorb, not intellectually though it is, but emotionally. The sheer scale of it, the strangeness, the fact that all of this is true, really true, not a story, not a myth, but the actual history of reality itself, and beyond them, more galaxies, and beyond those, more still, stretching in all directions, as far as you can see, as far as telescopes can see, as far as is physically possible to see, limited only by the speed of light and the age of the universe, the cosmic web, the large-scale structure of the universe, galaxies clustered along filaments, great strands of matter stretching across hundreds of millions of light-years, separated by vast voids, empty spaces where almost nothing exists. It looks like a spiderweb or a neural network, fractal, self-similar, beautiful in its complexity. You'd feel small here, impossibly small, not just physically, though you'd be tiny, a single human-sized speck in a universe 93 billion light-years across, but temporally, cosmically, you're a brief flicker, a momentary organization of atoms, a pattern that exists for a few decades, a century at most, and then dissolves. The universe around you has existed for 13.8 billion years. It will exist for trillions more, maybe forever. You're less than a heartbeat in its history. And yet, you're here. You're aware. You're conscious. You can see this, understand this, feel the weight of it, the vastness, the age, the beauty, the indifference. The universe doesn't care about you, doesn't even know you exist, but you know the universe exists, and that knowledge, that awareness, that capacity to wonder, that's something. In a universe that's mostly unconscious, mostly unaware, mostly just following blind physical laws. Consciousness is precious, rare perhaps, possibly unique to Earth, possibly common, we don't know yet, but precious. You are the universe looking at itself, thinking about itself, wondering, and when you're gone, when your atoms scatter and return to the cycle, that moment of awareness will have been real. Brief, yes. Temporary, yes. But real. And that's enough. Let's come back now. Gently, slowly. From the space between galaxies back to the Milky Way. From the Milky Way back to the solar system. You don't have to understand every detail. You don't have to remember the numbers or the time scales. Just let it wash over you. Let yourself feel the vastness of it, the age, the patience of the universe. 13.8 billion years. From the solar system back to Earth. Back to this small blue-green world, orbiting an ordinary star, in an ordinary galaxy, in an ordinary part of the universe. But extraordinary nonetheless, because it's home. Earth is special, not cosmically, not in any objective sense. There are probably billions of planets like it, maybe trillions. We're finding more all the time, rocky worlds in the habitable zone, with liquid water, with atmospheres. Earth is, in all likelihood, not unique, but it's special to us, because it's ours, because it's where we are, because it's where life, our form of life at least, emerged and thrived and evolved into countless species, including us. Look at Earth from space, that famous image, the pale blue dot photograph taken by Voyager 1 in 1990 from about 6 billion kilometers away. Earth is a single pixel, less than a pixel, a speck of light, suspended in a sunbeam. Everything that's ever happened in human history happened on that speck. Every war, every discovery, every work of art, every act of kindness and cruelty, every love affair, every birth and death, all of it on that tiny, fragile dot. Carl Sagan, reflecting on that image, said, "That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam." And he was right. We're small, fragile, temporary, but we're here. And for now, this tiny speck is all we have. Take care of it. Not because it's cosmically significant, not because the universe will care if we destroy it, but because we care. Because we live here. Because everything we love is here. The forests and oceans, the mountains and deserts, the animals and plants, the people, all of it, on this one small world, precious, fragile, irreplaceable, at least for now. And while you're here, while you're alive, while you have this brief moment of consciousness, be kind, be curious, be present. And it all led here, to this moment, to you, listening to this, breathing quietly, existing. You are part of this story, made from it, woven into it. Every atom in your body was born in the Big Bang or forged in the heart of a star. Notice the beauty, the small things, the light through the trees, the sound of rain, the warmth of the sun on your skin. Connect with others, love well, help when you can, forgive when you can, be gentle with yourself and others. None of it will echo through eternity. None of it will change the trajectory of galaxies, but it will matter here, now, to you, to the people around you, and that's enough. The universe is vast, ancient, indifferent, but you're not. You're warm, you're alive, you care. You create meaning in a meaningless cosmos. You create beauty in an indifferent void. You create love and connection and purpose where none exists objectively. And that's extraordinary. That's the miracle. Not that we exist. Existence is easy. The universe is full of matter and energy. But that we're aware, that we care, that we create meaning, that we look at the stars and feel wonder, that we look at each other and feel love, that we're here, now, fully, briefly, beautifully. It's been a long journey, from the Big Bang to now, from the first instant of time to this instant, 13.8 billion years, compressed into a few hours, a few thoughts, a few words, all of it leading here, to you, to this breath, to this quiet moment. The universe is still expanding, still cooling, still evolving. Stars are still forming in distant nebulae. Planets are still coalescing from disks of dust. Galaxies are still colliding, merging, creating new shapes. The story continues. It always continues, but for now, rest. You don't need to carry the weight of it all, the vastness, the age, the eventual ending. You don't need to understand everything. You don't need to remember every detail. You just need to be here, now, in this moment, which is all any of us ever have. Close your eyes if you haven't already. Feel the weight of your body, the surface beneath you, supporting you, holding you. Feel the air moving in and out, slow, easy, natural. You are the universe, looking at itself, through your eyes, through your mind, through your wonder and curiosity and awe. For a brief moment, cosmically speaking, just an instant, the universe is awake. The stars are still shining out there in the darkness. Billions of them, trillions of them, more than can be counted, each one a sun, each one burning hydrogen, creating light, creating warmth, creating the elements that make planets and life possible. They don't know you exist, they don't care, but they're there, constant, patient, shining, and their light reaches you, crosses vast distances, takes years, centuries, millennia to arrive, and touches your eyes, your skin, your world. You're connected to them, made of them, part of them, stardust, supernova ash, cosmic recycling. You are the universe. Let yourself rest now. Let the universe continue its work without you for a while. Let the stars burn. Let the galaxies turn. Let time flow steady and patient like it always has. You've done enough for now. You are enough. Breathe, slowly, deeply, fully. Feel the rise and fall of your chest. Feel the life in you, the consciousness, the awareness. This brief, beautiful moment of being awake in an otherwise sleeping cosmos. You matter, not to the universe perhaps, not cosmically, but to yourself, to the people around you, to this moment, and that's all the mattering that's needed. Rest, let go, let yourself drift, into sleep if that's where you're headed, or into peace, or into whatever comes next. The universe will still be here when you return. The stars will still be shining. The earth will still be turning. Time will still be flowing, and you'll still be part of it. For as long as you have, for as long as this beautiful temporary moment lasts. As the universe expanded and cooled, things began to happen. Structure began to emerge from the chaos. In the first microsecond, 1/1,000,000th of a second, the temperature had dropped to about 10 trillion degrees. Still unimaginably hot, but cool enough for something new. Quarks. The cosmos is vast, but you are here, and for now, that's enough. Peace, stillness, silence. These are the fundamental particles that make up protons and neutrons. They condensed out of the cooling energy like droplets forming from steam. Up quarks, down quarks, strange quarks, charm, top, bottom. 6 types in total, each with different properties, each playing a role in the structure of matter, to the moment when there was no space, no matter, no light, no stars, no galaxies, no planets, no atoms. And then, in an instant so brief it defies comprehension, there was the Big Bang, the birth of everything. They appeared, flickered, collided, combined, separated. The universe was a seething soup of particles and antiparticles, energy and matter, Creation and annihilation happening everywhere, all at once. It was chaos. Beautiful, creative chaos. But with rules. With laws. Physics was operating even then. The forces that govern reality, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, they were all there, shaping what could happen, determining what would survive. By the time the universe was 1 second old, 1 whole second, an eternity compared to what came before, something profound had happened. The quarks had combined. 3 quarks together make a proton, or a neutron, the building blocks of atomic nuclei, and electrons had appeared. Tiny, negatively charged particles that would eventually orbit those nuclei, forming atoms. The basic cast of characters was assembled, the pieces that would eventually make everything else. But they weren't organized yet. No atoms, no molecules, just particles, freely roaming through space, colliding, scattering, heated by the intense radiation that filled the universe. It was still too hot for anything stable. Any structure that tried to form would be immediately torn apart by the violence of the environment. But the temperature kept dropping. The universe kept expanding. And about 3 minutes after the Big Bang, something beautiful happened. 3 minutes? Think about that. In 3 minutes, you can make a cup of tea, walk to the corner store, listen to a song. In the first 3 minutes of the universe's existence, the temperature dropped from incomprehensible heat to only 1 billion degrees, cool enough for nuclear fusion. Protons and neutrons floating through space began to stick together when they collided. 1 proton plus 1 neutron makes deuterium, heavy hydrogen. Deuterium plus another proton makes helium-3. Helium-3 plus another neutron makes helium-4, regular helium. This is the same process that powers stars, nuclear fusion, the combining of light elements into heavier ones, releasing energy in the process. And in those first few minutes, it happened everywhere, throughout the entire universe. Trillions upon trillions of fusion reactions, all at once. And from that first moment, that impossible, explosive, creative moment, everything that exists, every atom in every star, every drop of water in every ocean, every breath you've ever taken, every thought you've ever had, all of it began its journey through time. Take a breath now if you'd like, a real one, slow and deep. Feel your lungs expand. Feel the air fill your chest. By the time the universe was about 20 minutes old, the temperature had dropped too far. Fusion stopped, and the universe had its first chemical composition, about 75% hydrogen, about 25% helium, tiny traces of deuterium, helium-3, and lithium. That's it. 3 elements. Well, 5 if you count the isotopes, but essentially just hydrogen and helium. Every other element, carbon, oxygen, iron, gold, uranium, would have to wait. They'd be made later, in stars. But the basic ingredients were there. The raw materials, ready to be shaped by gravity and time into stars, galaxies, planets, and eventually, life. Take a moment with that. The universe, at 20 minutes old, contained all the hydrogen that would ever exist. Every hydrogen atom in every star, every drop of water, every molecule of methane on Titan, every bit of hydrogen in your body. It was all made in those first 3 minutes. 3 minutes of creation that would supply the universe for billions of years. But the universe wasn't done yet. Not by a long shot. It was still incredibly hot, still filled with a thick fog of particles and radiation. Light couldn't travel freely. Any photon, any particle of light that tried to move would immediately collide with an electron or a nucleus and scatter in a new direction. The universe was opaque. Glowing, yes, but opaque. Like being inside a star. Everywhere you looked, just blinding light, scattered and diffused. This continued for a long time. Thousands of years, tens of thousands, hundreds of thousands. The universe kept expanding, kept cooling, growing larger, growing darker in a sense, though still far too hot for anything we'd recognize as cold. The temperature dropped from billions of degrees to millions, from millions to hundreds of thousands, from hundreds of thousands to tens of thousands, slowly, patiently, following the laws of thermodynamics, following the inexorable expansion of space, cooling like a hot coal left in the air. And then, about 380,000 years after the Big Bang, something beautiful happened. Something that would change everything. 380,000 years after the Big Bang. In human terms, that's a long time. Longer than recorded history. Longer than agriculture. Longer than cities. Longer than writing. But in cosmic terms, it's nothing. A blink. A heartbeat. The universe was still young, still finding its shape, still cooling from its violent birth, and then the temperature dropped below 3,000 degrees Celsius. Still hot. Hot enough to melt any metal, hot enough to vaporize rock, but cool enough for something new, cool enough for electrons to slow down, cool enough for them to be captured by atomic nuclei. Let your shoulders drop. Let the tension fade from your neck, your jaw, your forehead. Let the day settle behind you. Whatever happened today, whatever is waiting for tomorrow, it can wait. For now, there's just this quiet space, this gentle voice, this slow unfolding of time and space and wonder. For the first time, complete atoms formed. Hydrogen atoms, helium atoms, electrically neutral, stable. This moment is called recombination, though that's a bit of a misnomer, because the electrons weren't recombining with nuclei. They'd never been together in the first place. But the name stuck, and when it happened, everything changed. Suddenly the fog cleared. With electrons bound into atoms, there were far fewer free-charged particles floating around. Photons, particles of light, could finally travel without being scattered. For the first time in 380,000 years, the universe became transparent. Light broke free, streamed out into space, travelled across the expanding cosmos, unimpeded, filling the universe with radiance. It was the first dawn, not sunrise. There was no sun yet. But the dawn of transparency, the moment when looking became possible, when light could journey across vast distances without interruption. If there had been eyes to see it, and there weren't, not yet, not for billions of years, they would have witnessed a sky full of glowing gas, gradually fading from white-hot to red to orange to darkness, the afterglow of creation, the last light from the hot, dense phase of the universe's infancy. And that light is still here, right now, all around you, everywhere in the universe. It's been travelling through space for 13.8 billion years, stretched and cooled by the expansion of the universe. When it was released, it was visible light, orange and red, like the glow of hot metal. But as the universe expanded, the wavelength stretched. The light redshifted, shifting toward longer wavelengths. Red became infrared. Infrared became microwave. Now 13.8 billion years later, it's microwave radiation, invisible to the eye, but detectable with the right instruments. We call it the cosmic microwave background, the CMB. The CMB was discovered by accident. In 1964, two scientists, Arno Penzias and Robert Wilson, were working with a large radio antenna in New Jersey. They were trying to measure radio signals from space, but they kept detecting an annoying hiss of static. No matter where they pointed the antenna, the hiss was there. Same intensity, same frequency, coming from every direction equally. At first, they thought it was a problem with their equipment. They checked everything, recalibrated, even cleaned out pigeon droppings that had accumulated inside the antenna, thinking the birds might somehow be causing the interference. But the hiss remained. Uniform, persistent, unavoidable. They didn't know what it was. But other scientists working on theoretical predictions realized what they'd found. The echo of the Big Bang, the afterglow of creation still ringing through the cosmos, ancient light, the oldest light there is. We're going to move through billions of years together, through ages so vast they make human history look like a single heartbeat. But we're going to do it gently, peacefully, like watching clouds drift across an infinite sky, or waves roll onto a shore that's been there for millions of years. Think about that for a moment. The universe remembers its birth. It carries the evidence with it, written into the very fabric of space, into the distribution of galaxies, into the ratios of elements, into that faint, all-pervading glow that fills the universe. We can look back in time. We can see, not with our eyes, but with instruments, almost to the very beginning. We can map the temperature variations in the CMB, tiny fluctuations, just a few millionths of a degree, but enough to show us the seeds of structure, the slight overdensities that would eventually become galaxies and clusters and superclusters. We can measure the expansion rate of the universe, the density of matter and energy, the curvature of space. We can test our theories, verify our predictions, and again the evidence points to the same story. The Big Bang happened. It's not speculation. It's not philosophy. It's history. The actual measurable, verifiable history of everything. If you could somehow tune a radio to the right frequency, around 160 gigahertz, you'd hear it. That faint hiss, the echo of creation. About 1% of the static between radio stations is actually cosmic microwave background radiation. Ancient photons released 380,000 years after the Big Bang, finally reaching your antenna after travelling for 13.8 billion years. You can hear the Big Bang, not directly, it's been stretched and cooled beyond recognition, but it's there. A whisper, a memory, a ghost of the universe's violent birth. After recombination, after the universe became transparent, things quieted down. The light faded, the expansion continued, the temperature kept dropping, and the universe entered what astronomers call the Dark Ages. Not dark in the sense of evil or bad, dark in the sense of lightless. The glow from recombination was fading, redshifting, disappearing into the infrared and beyond, and there were no new sources of light, no stars yet, no galaxies, no quasars or supernovae or glowing nebulae, Just vast clouds of hydrogen and helium drifting through space, cooling, expanding, spreading out across the growing universe. It must have been eerie, in a way, empty, quiet. The universe was there. Atoms, dark matter, radiation. But nothing was shining. Nothing was creating new light. Just darkness. And in that darkness, gravity was working. There's nowhere else you need to be. Nothing else you need to do. No one waiting for you to be anything other than what you are right now. Just settle in. Let the world fade. Just a little. Gravity is patient. It doesn't push. It doesn't shove. It just pulls. Gently. Persistently. Every particle in the universe attracts every other particle. The attraction is weak, absurdly weak at small scales, but it's always there, always working, never tiring, and over time it adds up. The universe wasn't perfectly uniform. There were slight variations in density, tiny ripples left over from quantum fluctuations in the first instant of inflation. Some regions had a little more matter, others a little less, and gravity amplified these differences. Regions with more matter attracted even more matter, slowly, imperceptibly at first, but steadily. Over millions of years, these denser regions grew denser. They began to collapse under their own weight. Gas fell inward, compressed, heated, and deep in the hearts of these gathering clouds something was building. Pressure, temperature, density, something that would eventually change everything. Take a breath. We're about to witness something extraordinary. The lighting of the first star, the end of the Dark Ages, the moment when the universe, for the first time in 100 million years, created new light. About 100 million years after the Big Bang, maybe 150 million, we're not entirely sure, the first star ignited. We don't know where it was, we'll never see it directly. It lived and died billions of years before our solar system even formed. Its light, if any remains, is scattered and lost among trillions of other stars, but we know it happened. Because we see the results. We see the heavy elements it created. We see the second and third generation stars that formed from its remnants. And we understand the physics. We can calculate when and how it must have occurred. Somewhere in a cloud of primordial gas, pure hydrogen and helium, untouched, as fresh as the universe itself. Gravity pulled enough material together. A clump formed, dense enough to start collapsing under its own weight. As it collapsed, it heated up. The atoms falling inward, picking up speed, colliding more and more violently. The center grew hotter, denser. The pressure built. 10,000 degrees, 100,000, 1,000,000, 5 million, 10 million, and then 15 million degrees Celsius, the temperature at which hydrogen fusion begins. Let your breathing slow, and let's begin. At the very beginning, the moment before moments, the silence before sound, the nothing before everything. Hydrogen atoms, protons really, since the electrons had been stripped away by the heat, began to slam into each other with enough force to overcome their natural repulsion. They fused, combined, became helium, and in that fusion, mass was converted to energy. E equals mc squared. Einstein's famous equation. A tiny amount of mass becomes an enormous amount of energy. The energy poured outward. Radiation, light, heat, pressure. And for the first time in 100 million years, a new light entered the universe. A star was born. Imagine that moment. For 100 million years, the universe had been dark, cool, quiet. Just clouds of gas drifting, slowly gathering, pulled by gravity into larger and larger clumps. And then a spark, a glow, small at first, flickering, uncertain but growing, brightening, stabilizing, a point of light in the darkness, blue-white, brilliant, hot beyond measure, the first star. That first generation of stars, astronomers call them population 3 stars because we've never actually seen one, were different from any stars we see today. They were enormous, massive beyond anything that forms in the modern universe. Why? Because they formed from pure hydrogen and helium. No carbon, no oxygen, no heavier elements. Those didn't exist yet, and without those heavier elements, the gas clouds couldn't cool as efficiently. They couldn't radiate heat away as easily, so they stayed hot, and hot gas resists compression. The only way to overcome that resistance was to gather enormous amounts of mass, dozens of times the mass of the Sun, maybe hundreds. These stars, when they finally formed, were monsters, bright, blue, incredibly hot, burning through their fuel at prodigious rates. A star like our Sun can burn for 10 billion years. These first stars burned out in just a few million years. They lived fast, brief, violent lives. But in that brief time, they changed everything. The light from these first stars streamed out into the darkness. Ultraviolet radiation, high-energy photons, ionizing the hydrogen around them, stripping electrons from atoms. They carved out bubbles of clear space, spheres of ionized gas, glowing faintly, expanding outward as more and more atoms were affected. And then more stars formed. Nearby, from the same clouds, clusters of them, dozens, hundreds, all massive, all bright, all pouring energy into their surroundings. Their light overlapped, the bubbles merged, and slowly, over tens of millions of years, over 100 million years, the entire universe was reionized. Close your eyes for a moment if you can. Try to imagine nothing, not darkness, not emptiness, not a void, but true nothing. No space for darkness to fill, no container for emptiness to occupy, no you to observe the void, just nothing. The dark ages ended. The universe filled with light, not bright light, not like day on earth, more like a dim, diffuse glow, scattered and subtle, but light nonetheless. The cosmic renaissance, the epoch of reionization, the universe waking up, and those massive first stars, they died, quickly, violently. When a massive star exhausts its fuel, it can't support itself anymore. The outward pressure from fusion, which had been holding the star up against gravity, disappears. The core collapses. In less than a second, it compresses from something the size of Earth to something the size of a city. The density becomes incomprehensible. Protons and electrons are crushed together, forming neutrons. And then the collapse stops, rebounds. The outer layers of the star, falling inward at a significant fraction of the speed of light, hit the rigid core and bounce back. A shock wave rips through the star. The star explodes, a supernova. For a few weeks, a single dying star can outshine an entire galaxy, billions of times brighter than the Sun. Visible across unimaginable distances, a beacon, a funeral pyre, a testament to the violence and beauty of stellar death. But from that death, creation. In the extreme heat and pressure of the supernova, temperatures exceeding billions of degrees, New elements are forged: carbon, nitrogen, oxygen, silicon, iron, all the elements heavier than helium, all the building blocks of planets, of life, of everything complex and interesting in the universe. They're made in stars, forged in fusion, scattered by supernovae. Every atom of carbon in your body was made inside a star. Every atom of oxygen you breathe was made inside a star. Every atom of calcium in your bones, every atom of iron in your blood, every atom of phosphorus in your DNA, all of it came from stars, from ancient suns that burned billions of years ago, then died in spectacular explosions, scattering their enriched material into space. You are made of stardust, not metaphorically, not poetically, literally, truly, physically. You are the ash of long-dead stars gathered by gravity, organized by chemistry and biology into something that can think and feel and wonder. You are the universe, made conscious. The remnants of those first supernovae drifted through space, expanding, cooling, mixing with the primordial hydrogen and helium, enriching it, adding complexity, adding possibility. And when the next generation of stars formed, population 2 stars, they contained those elements,